Welcome, students. This is Basic AI Concepts and Terminologies. We are going to go over some of just the fundamentals of AI just to kind of get you started. We're going to meander a little bit around things like why artificial intelligence matters. Why does AI matter? Why do we care? Why do we care about AI-powered applications? What's important to them? What effect, what improvements can they have for us? And this is all, by the way, still in service of the AWS, certified AI practitioner certification. This fundamental understanding is necessary to really understand how to approach the certification. So, for example, we like AI-powered applications for things like healthcare, for finance, for retail. And the reason this matters is that what we're looking for is that force multiplier of improving efficiency, reducing operational costs, as well as just enhancing decision-making and our capability to get to decisions faster. Now, businesses absolutely love artificial intelligence and all of its derivatives because you can use AI to automate really complex tasks, but also interaction tasks like customer service, fraud detection, and data analysis. Now, all of this is to say is that we're trying to basically enhance the customer experience while reducing the human workload. And so the demand for AI skills is growing because it's basically allowing businesses to gain insights and make faster data-driven decisions. So, everything from AI-powered chatbots to, data analysis to writing code, basically is an attempt to act as a force multiplier by helping humans deliver things better, faster, quicker. Now, as you can imagine, AWS is invested in this in particular with services like SageMaker and Rekognition, which of course SageMaker does machine learning, lots of machine learning subservices, and Rekognition is an image recognition service. And the reason this is taking hold is that this is all enabling even normal users to get access to information, data, tools, and categorizations that normally they wouldn't even have access to. And part of the reasons why businesses are really excited about this is that we're moving away from traditional rule-based software engineering, and we're focusing more and more, particularly since 2016, 2015, around machine learning-based systems, which are systems that do not require rules. They can learn the rules based on the data they're trained on and the data they're exposed to. Like rule-based systems, for example, operate on a predefined rule set of logic. So it's ideal in situations where the inputs and outputs need to be consistent. For example, like approving loan applications with, people with a credit score above 750. This is simple, straightforward. It really doesn't require the advanced capability of a machine learning system. ML and AI systems, by the way, on the other hand, are probabilistic and can adapt to data over time, even data they haven't seen before based on past data they've seen, which allows them to make probabilities or prediction statements based on patterns, complex data sets. And so it really, if a business needs simple, repeatable outputs, then a rule-based system is going to be more cost-effective. But if you want something that can make things like recommendations and predictions and forecasts, machine learning is going to be your friend. Now, artificial intelligence is officially defined as a branch of computer science that's focused on creating systems that are capable of performing tasks that typically require human intelligence. Now, that's a big mouthful. We've basically had artificial intelligence for decades. Everything from calculators, anything that replaced human effort could be, in a sense, considered to be artificial intelligence. Now, is it true sentient, general artificial intelligence? No. But the rubric of artificial intelligence has included anything that has supplanted and or assisted human effort. Now, artificial intelligence, as it's defined today, includes things like visual perception, speech recognition, decision-making, and language translation, because we've gotten way more advanced in how we've approached these topics. So we're moving beyond just simple calculators to actually advanced human capabilities more and more and more. Now, AI in itself is a huge field and has various subfields, of which machine learning is one of these, as well as deep learning. Now, with this in mind, not only are there subcategories, but we in general think of AI in two categories. We think of it as, is it narrow AI, meaning it's focusing on specific tasks, right? Versus broad AI, where it's basically AI with broad problem-solving abilities, much like a human being, which is why generative AI is exciting because it's leaning us towards that direction. An example in this case would be like AI could help radiologists read x-rays faster, or it could basically make product recommendations like we see on Amazon. And so when we talk about narrow AI, we are talking about things like very narrow, like interactions, right? Directions, video recommendations, product recommendations. And of course, all the vendors that are listed there do that. Now, general AI, different from generative AI, right, is basically a theoretical form of AI with broad problem-solving abilities. We are starting to see hints of that with generative AI, but we're not quite there yet as far as the broadest definition, but we're moving in that direction. So as we mentioned before, healthcare is one of the great fields for this, retail recommendations. And so artificial intelligence in general kind of leans into this space where we can basically either find out whether something is in or out of a classification, so like binary classification, or whether probabilistically someone is likely to buy or not buy, or whether something is predicted to go up versus down. And so as we do more and more of this, what we're actually talking about is a subset of AI called machine learning. And machine learning basically uses math, algorithms, and statistical models to basically allow us to learn from both structured and unstructured data. So data that is labeled, data that is, unstructured and structured, data that is unlabeled. And it can actually learn the patterns of the data it's fed. And when it sees something new, it can apply that pattern to the new object. This is very different from following explicit instructions. Now what we have is something that approaches more of the way that we do pattern recognition. And so ML models will improve over time as more accurate feedback and data is provided to them. This is key because machine learning basically uses that math to define patterns in things like training data, which then gets validated through test data. Because if you want to train, for example, a machine learning algorithm to identify a dog versus a cat, you have to provide confirmed labels for both. You have to train it to know the difference between what a cat is and what a dog is. Now, many times you can just do that through some kind of vector image kind of analysis, but the idea is that what are the patterns and predictions that it can make so that it can, with a high level of accuracy, predict whether a picture is a dog or a picture is a cat. And the training data is important because that training data needs to be accurate, consistent. It has to basically be able to be used to teach the model so that it can get to proper patterns and predictions. So, for example, email services like Gmail, for example, use specific patterns to detect and filter out spam emails. Chatbots are also going to learn from interactions and grow, especially if there's a positive, thumbs up feedback for an interaction, then they're more likely to do that interaction next time in a chat. Now, if AI wraps around machine learning, then deep learning is even a deeper subset of ML, and this actually uses math in conjunction with other math. So think of, in a sense, algorithms, connected to other algorithms, right? So it creates these multi-layer like neural networks, somewhat modeled in the way like the human brain works, right? And the idea here is to solve more complex problems. And so if you can visualize this, think about like you've gotten some input, you've gotten some data. Let's say it's a cat picture. And you analyze the cat picture and you realize that the ears are sharp and the snout is flat and the eyes have a certain shape to them. What happens is that input layer then gets translated through a bunch of math that basically says, oh, you know what? If it has triangular ears and it's got a flat snout and it's got those special cat eyes, well, then it might be a cat picture. And I'm this confident that it's a cat picture. And so I'm kind of simplifying it, but like the neural network, the math there, it's almost like a decision tree of math of like, how do I weight this? How important are the ears being triangular? How important are the eyes having specific shape or a specific color? And so in a neural network, this is just artificial nodes or neurons. And what they do is they process the input data through various layers. And we're just showing 3 here. There could be a lot of hidden layers. And so by doing this level analysis, you've got real-time voice assistance, real-time facial recognition. You've got language translation. And this is where deep learning really excels, is in really high-quality analysis of inputs to outputs. This could be anything from speech recognition to image recognition to a lot of different applications. Now, if we visualize this, artificial intelligence is basically a general bucket for anything that can, in a sense, replace human effort. It can do a little sense, a little reason, and act and adapt. That's like your general thing, but we've kept it very simple in the last few decades. Machine learning starts to get very specific by using very specific algorithms who can be trained to identify patterns and make predictions and outcomes. Deep learning is a subset of that, in which machine learning is a multi-layered neural network with math, in a sense, connected to math, with input layers, hidden layers, and output layers. And so those are the basic concepts of artificial intelligence and machine learning and deep learning all conjoined together. Okay, so in understanding AI, ML, and deep learning, which each of these is a subset of the other. So machine learning is a subset of AI and deep learning is a subset of machine learning, right? And so artificial intelligence is basically a broad field that involves creating machines or systems that are capable of basically performing tasks that normally require human intelligence. This includes reasoning, learning, problem solving, perception, language understanding. And the focus here is that it's all about basically driving autonomy, computer and machine autonomy inside of different industries. So it's really about driving automation somewhere. It does actually enhance productivity. And AI encompasses a wide range of technologies and approaches. And this could be everything from simple rule-based systems to complex algorithms, because this is the foundation by which pretty much all machine learning and subsequently deep learning sit, right? And this can include robotic, autonomous vehicles. Remember, its main goal has a general goal, is we want to simulate human intelligence in machines. Now, machine learning has a subset, is basically a subset of AI that focuses on developing algorithms, basically mathematical formulas that enable computers to learn from and grow, to make basically decisions based on data. They are very much data-driven. They learn from data patterns. And the idea is to make predictions, and the more accurate data and the more data they have, the more likely they are to make what they call an inference or a prediction. Now, there are different kind of learning types, which we'll go through later, such as supervised learning, unsupervised learning, reinforcement learning. We'll go through all that. But the key concept is that it is all about the algorithms. This includes decision trees, vector machines, clustering, all these algorithms that basically allow us to make predictions. And there's also a lot of feature engineering. So like spam systems, fraud detection, predictive maintenance, that's really where machine learning thrives. Now, deep learning is a specialized subset of machine learning, and it uses these multi-layered neural networks, right, to model basically complex patterns in data. So these neural networks, by the way, are insist of the human brain. They're interconnected nodes. You saw a picture in our last video about this. And they learn representations of data at like multiple levels of abstraction. So they require larger data sets than machine learning and significant computational power. And there are all kinds of neural networks, right, that make up deep learning. There are convolutional neural networks. They're recurrent. There's generative adversarial networks. There's all kinds of networks. And these are all about speech recognition, facial recognition, natural language processing, complex, high accuracy, basically reasoning is what we're looking for. So think of AI as the umbrella term, ML is the subset, DL is the subset of that. And it's basically, ML and deep learning in particular rely heavily on data models to train the algorithms and to improve accuracy. So here's another picture of this. Deep learning's inside machine learning, artificial intelligence sits there. Now, key differences, again, just to make sure that we're clear. Artificial intelligence is basically general application of human reasoning to machines with a goal towards automation. Machine learning is going to basically do predictions from data patterns, and deep learning is going to do complex pattern recognition with these neural networks. So how do you know which to choose? Well, usually what we're talking about is the difference between something, say, like machine learning, which is ideal for simpler tasks requiring like predictive analysis, like will this person buy, right? versus deep learning, which is like, I need to coordinate multiple object recognition, velocity type, like autonomous driving, right, as an example. That's really deep learning, where it's going to require a lot of complex, large-scale data that you're going to need to make a specific, precise decision about. Now, the data needs are obviously very different. Machine learning still requires a moderate amount of data and moderate amount of resources. Deep learning typically requires a lot more. In essence, deep learning is more precise, but there's a computational and a data size cost for that. So, depending on the problem, one might opt for traditional AI methods, ML algorithms, or DL techniques, right? And also depends on the limitations of the data you have and the computational power you have, right, at your fingertips. Let's talk about the different types of inferencing that you can run into when it comes to basically making predictions. So let's talk about it. Let's talk about inferencing, and let's talk about two basic types, the kinds of inferencing that you're going to run into. So inferencing in AI, we keep saying things like models or inferencing, and this can be misleading. So let's talk about this. Inferencing is the process. This is the use of trained AI models to generate predictions or classifications based on the data that has been input. Now, in other words, you've trained a model to make a prediction, and so you give it another piece of information and ask it to apply the model. So what does that mean exactly? An inference is basically a prediction, right? It's a classification, it's an output. And so what happens is that you've got a piece of math, like a type of algorithm called a model, that does a certain thing. Maybe it classifies. It says, yes, this will happen. No, this won't happen. Maybe it makes a new numerical prediction. It's basically making a forecast, an inference, a prediction from historical data that it's seen before about a new piece of data. And so what happens is that the model gets trained, and then what it does is it can basically then make a probabilistic statement. It is very likely, highly likely, that this is going to happen. So for example, if this was a spam filter that had been trained on millions of emails about what was spam and what wasn't spam, when it saw a new email, it could make an inference or a prediction to determine if the new email that it just saw was spam based on the old emails it saw, right? And so inferencing is really the final application of a trained model's output. And so this allows inferencing to be the thing that the model does. This is what the math does, is it does fraud detection, it can do product recommendations, it can do customer service automation, because the model has been trained, and once it's reached a prerequisite level of training, it can then be allowed to make inferences, like it can be applied basically in production. Now there's two major types, general categories of inferencing that we see, which the first is real-time inferencing. And this is where it's making predictions or classifications right as the data arrives, right? It processes the input instantly. So in this case, let's say it's an email. It sees the email, classifies it as either spam or not spam, and returns the output in the quickest way possible. So this is crucial for applications that require immediate response. And so as you can see here, chatbots, fraud detection, autonomous driving systems, recommendations engines, like, for example, when you interact with like Alexa, right? That system's going to process your input in real time and generate a relevant response. And so SageMaker is basically the kind of bucket ML machine learning service that offers endpoints for deploying models that can perform real-time predictions or inferencing. And these SageMaker endpoints are highly scalable. They can handle multiple workloads, but they basically respond as quickly as they can. Now, the other type of inferencing is batch. And so in this case, the data doesn't just arrive in singles, it arrives in bulk. Rather than handling each data point as it arrives, the model basically aggregates a couple of inputs and then processes them all simultaneously. This method is a lot more efficient for scenarios where you don't need real time. And so this could be aggregation of data from like surveys, sentiment analysis on social media posts collected over, hours, days, or weeks, or, making predictions over data that were gathered over a larger amount of time, like, for example, stock market data, right? So SageMaker also supports batch inferencing through these batch transform jobs against these endpoints. And so this allows users to basically take larger data sets or even larger just kind of live inputs and pass them to SageMaker to have them processed in bulk. So to break this down a little further, right? Real-time inferencing involves making predictions instantly as the data is received. It's common in applications that require real-time feedback, real-time responses. And so this is essential for applications that require immediate feedback, like, hey, Alexa, what's the weather today? Alexa listens to you, basically does some processing, and then says, oh, you know what? Today the weather is sunny with a high of 25 degrees Celsius, right? This is what real-time inferencing is for, is this real-time interaction. Batch inferencing, in summary, involves processing large amounts of data at once in bulk rather than a piece one at a time. It's ideal for, like, again, large data analysis, overnight processing. And so the data is collected and processed in groups. This is great where immediate responses are not necessary. For example, where you've got a large amount of data like stock predictions, you need to process that data, and then in the morning you want to be able to predict, right? And this could be like stock, this could be customer segmentation, it could be fraud detection, although a lot of fraud detection does happen at least in real time. But then there might be a deeper analysis of fraud detection that you're going to do in bulk, like a secondary level, because you're looking for a pattern of transactions. This is great for when large-scale data analysis is required. So here it is again, just to make sure we're driving it home. Real time happens in real time, data in, data out, right? Batch inferencing, group of data happening over time, being processed and then being processed out. So that's the difference between batch inferencing and real-time inferencing. Real-time inferencing happens immediately. You are making predictions immediately as the data comes in. Batch, you are waiting until you have an aggregate of data over a period of time, and then you are running your predictions or your inferencing. Supervised, unsupervised, and reinforcement learning. These are different types of machine learning. So supervised learning, and we mentioned this, by the way, earlier in the context of labeled data. This is a model that learns from labeled data. This is data with known predictions or outcomes. And this is, for example, used for things like predicting house prices based on features like square footage, location, number of bedrooms, adjoining sales, or predicting stock market movements like historical data, right? Basically, supervised learning learns from labeled data, typically historical data. And then you've got unsupervised learning, which is all about finding groupings, clusters, anomalies, and patterns on data where you actually don't know what the prediction and the inference is, for example. So this isn't necessarily historical data per se, although it can be, but it's like being able to segment or group customers in marketing based on behavior that doesn't necessarily have predefined labels. This is also good for things like fraudulent activity, right? The third type is reinforcement learning. Now, reinforcement learning is super interesting. This is where you give a model a certain kind of system to play in, like a road. And through trial and error, it basically figures out either rewards or penalties. And this could be things like playing chess. It could be driving down a road. It could be anything that has a closed system to it where it can basically try things and fail. But there's like a bound box. Like it's like there's limits to it, because otherwise, if it's unlimited possibilities, it's hard to figure out through trial and error what the rewards and the penalties are, right? So, Go, I think, or chess is a great example of a bound system where reinforcement learning could go through and play. Even, for example, letting AI loose inside like an operating system, which, while large, has a bounded system to it, a set of boundaries, as long as it doesn't leave the network, could also be another great use of reinforcement learning. Now, to dive in this a little deeper, supervised learning, right? All about the models being trained on labeled data sets. That means both the input and the desired output, the inference, are known. So again, we're back to our cat and dog kind of analysis, where the model is going to look at that and it already knows what the right answer is, but after it's done the analysis. This could also work in spam detection. Is this spam or not spam? Based on past models. By the way, there might need to be like millions of labeled emails to make accurate predictions. And also it's got to adapt to spammers. So new data has to be added as the spammers, adapt to new techniques. This could also apply to predictions around things like credit score. Like, is this a high-risk person or a low-risk person based on income, credit history, employment, etc. And then there's unsupervised learning. And unsupervised learning does things like, oh, well, we have an input, like a picture, for example. And what we're trying to do is figure out where all the cats and the dogs are. Like, is this predominantly cats or is this predominantly dogs? Right? So we're doing some level of categorization or classification. Again, as our earlier statement referenced, you could do all kinds of groupings, clustering, segmentations. You know, is this a set of budget conscious buyers? Is this a set of premium buyers? The other thing is that when you don't have labeled data, you can do anomaly detection and say, well, this data all looks similar, but this data does not. And so that's more about like analyzing the data. And so like, for example, network traffic, you could do anomaly detection against the network traffic, which you're finding more and more happening inside of a lot of monitoring systems. And so when no labeling is required, the system's got to deal with, you know, false positives and continuously basically refine its ability to distinguish between what is above the line and what is below the line. And so that's unsupervised learning. Reinforcement learning is all about giving a bounded system and a set of rules, an environment basically for the algorithm to play in. And what it does is it's basically going to take an action, evaluate whether that action led towards something it wanted or something it didn't want, and then try it again, but with a different, you know, changed set of parameters. And so, like, for example, a recommendation engine, if you make a recommendation and then the person either thumbs ups it or watches it, based on what you know about that person, then you got feedback about whether that recommendation was good for that person or not great for that person. Here's another example. Traffic lights, right? I mean, that's a bound system. You want traffic to flow. Are you increasing traffic congestion and improving vehicle flow, or are you reducing it? And is it based on the timing? Do you have an understanding of what's stacked, what's not stacked in terms of cars, like, you know, kind of backing up, not backing up? And you only have a couple of actions. You either can make the lights red, yellow, and green in relation to each other. And so it's a great kind of bound system to kind of teach a reinforcement learning algorithm basically how to optimize traffic flow. And that is the summation, right, of supervised, unsupervised, and reinforcement learning. Basically the three major types of learning inside of an AI model. This is key, absolutely essential for the exam. So make sure you understand these concepts very well. Catch you in the next video.